In this video, we'll talk about sketching graphs. The basic question is simply, how do you sketch a graph of a function f? We have a method which is based on information that we can obtain from the first and second derivative. But we start with 1. Plot any x-intercepts or y-intercepts and mark any vertical asymptotes. This is usually the easiest part. Step 2. Find the critical numbers of f, or the critical points. C1, C2, C3, and so on. These are the places where the first derivative is either 0 or doesn't exist. We're interested in these because these are the x values for local extreme values, local maximums and local minimums. Now you might get a few extra points in there where the tangent line is horizontal that aren't local maximums or local minimums, but that will still help you determine the shape of the graph. For 3, we compute the outputs that correspond to these critical numbers. So C1, C2, C3, those are the x values. The y values are what you get when you plug these x values into the original function. F at C1, F at C2, F at C3, these give you the y values. Now you can plot the points C1, F at C1, C2, F at C2, C3, F at C3, and so on the graph. The c values are the x values, and the f at c, those give you the y values. Now, the next step is to check where f is increasing or decreasing by making a sign chart for the first derivative. And number 6, we can check the concavity by making a sign chart for the second derivative, f double prime. You put all of this together and basically connect the dots. Then you also want to determine the limits as x goes to infinity or x goes to negative infinity. These will give you the asymptotic behavior of the graph. Perhaps there's a horizontal asymptote, perhaps the functions are unbounded. These are things that you want to know when you're trying to sketch the graph. Let's go ahead and look at an example. Let's sketch the graph of the function f at x equals x divided by x squared plus 4. The only intercept is the origin, the point 0, 0. There are no vertical asymptotes for this function. Next, we want to compute the first derivative. This will give us the critical numbers, or the critical points. F prime at x is equal to the derivative with respect to x of this quotient. So we have to use the quotient rule. We've left out the details here, but if you use the quotient rule, it will simplify to 4 minus x squared divided by x squared plus 4 raised to the second power. And you can see that this derivative is equal to 0 when x is equal to 2 or when x is equal to negative 2. We can just factor the numerator to get that. 2 minus x times 2 plus x. And of course this is divided by x squared plus 4 over 2. There are no places when this derivative doesn't exist. You're never dividing by 0 because x squared plus 4 is always positive, so you're never dividing by 0. So the only two critical points that we get are when the derivative is equal to 0, at x equals 2 and x equals negative 2. So we can make a little sign chart. So here's our sign chart. You mark the zeros of the derivative, x equals negative 2 and x equals 2. We can now complete the sign chart. It's already been done for us, but we can just double check. If you take some number to the left of negative 2, like, for example, negative 3, then you'll have 2 minus negative 3 is positive 5, and then that will be multiplied by 2 minus 3, which is a negative 1. So you'll have a negative number in the numerator. The denominator is always positive, so the result will be negative. We can also pick something between negative 2 and 2. For example, pick x equals 0. Then we're going to have 2 times 2, which is positive, divided by a positive number. So that's positive. Finally, if we pick something bigger than 2, say 3, we'll have 2 minus 3, which is negative 1, times 5, divided by something positive. So that's negative, so we'll have a negative number. So we've determined now that the derivative is negative, and then passes through 0 and becomes positive, and then passes through 0 and becomes negative again. So our function is first decreasing until x gets to negative 2, then increasing until x gets to positive 2, and then decreases after that. Since the function changes from decreasing to increasing at negative 2, we can see that there's going to be a local minimum at x equals negative 2. And the function changes from increasing to decreasing at positive 2, so that's going to give us a local maximum. So these will be useful when we're trying to graph it. So we want to come up with the actual y values, and that's easy enough to do. You can just plug in x equals negative 2 and x equals positive 2 into our original function. When x equals negative 2, you end up with negative 2 over 8, which is a negative 1/4. And when x is positive 2, you end up with 2 over 8, which is a positive 1/4. The next step is to determine the concavity, so we can compute the second derivative. Again, we have to use the quotient rule, but if we do and simplify the result, we end up with 2x times x squared minus 12 divided by x squared plus 4 cubed. Again, you don't have to worry about dividing by 0 because x squared plus 4 is always greater than or equal to 4, so you're never dividing by 0. There are 3 places where the second derivative is equal to 0, at x equals 0, and also at x equals plus or minus the square root of 12, which you see here. So we can check the concavity by making a sign chart for the second derivative. We have to mark on a number line the places where the second derivative is equal to 0, negative square root of 12, 0, and square root of 12. And you can just check a point on each of these 4 intervals. So we know that the square root of 12 is approximately 3.4. So if, for example, you pick some large number, some number bigger than 4, then what are you going to have? So if we're on this interval, you could pick, for example, x equals 10. Then you'll have 20 times 100 minus 12, which is certainly positive. The denominator is always going to be positive because it's x squared plus 4. So you'll definitely end up with something positive here. Between 0 and the square root of 12, you can pick something small like 1. So then you'll have 2 times a negative 11. So that will be negative. If you pick negative 1, then you'll end up with a negative 2 again times negative 11. So you'll have a negative times a negative is a positive. Again, the denominator is always positive. And now for this last interval, you just want to pick something less than negative 3.4641 or thereabouts. So you could pick something like a negative 10. Then you'll have a negative number, negative 20, times, again, this will be 100 minus 12, so that'll be positive. So you'll end up with a negative value. So that tells you that you have a function which is concave down until negative square root of 12, then it's concave up until you get to 0, then it's down, and then at the square root of 12, it changes to concave up again. So that tells you you have 3 inflection points. So the concavity changes at these 3 points, and as I mentioned, these places where the graph changes concavity, they're called points of inflection or inflection points. Inflection points happen at x values in the domain of f, where f double prime equals 0, or where the second derivative doesn't exist. But as usual, not every such x gives a point of inflection. More generally, points on the graph where the behavior of the graph changes are called transition points. Points of inflection are transition points. Points of local extrema are also transition points because those are places where it changes from increasing to decreasing or from decreasing to increasing. The final piece of information we need to graph this function is the behavior as x goes to infinity or x goes to negative infinity. What we can show is that both of these limits are 0. So the limit as x goes to infinity of x over x squared plus 4 is equal to 0, and also the limit as x goes to negative infinity of x over x squared plus 4 is equal to 0. This means that the x-axis is a horizontal asymptote for the graph. Now, why is this true? Well, as x goes to infinity, x is growing large, but x squared plus 4 is growing much, much larger. So the denominator dominates over the numerator. And that's why you end up with something which is close to 0. And the limit actually is 0. So that basic idea is that as x is going to infinity, this plus 4 barely even affects anything. So really what you're looking at is x divided by x squared, which is like 1 over x. So when x is really large, your value looks like 1 over x, which is getting close to 0. Here's a graph of y equals x over x squared plus 4. As you can see, when x is negative, the function is decreasing up until the point that you get to the first critical point, which is right here. That's at x equals -2. And then the function starts increasing until you get to your second critical point, which happens at x equals +2. And then your function starts decreasing. You can also see that the function far to the left is concave down, and then it turns into concave up, then it switches to concave down, and then concave up again. All of these features we knew that it would have because of the first and second derivative. Also, it has a horizontal asymptote at y equals 0, the x-axis. In general, we determine the horizontal asymptotes of a rational function, if it has any, by computing the limits as x goes to infinity and as x goes to -infinity. For rational functions, we can divide the numerator and the denominator by x raised to the largest power that appears in the denominator. So for our example, we can show that the limit as x goes to infinity of x over x squared plus 4 is equal to 0 by dividing the numerator and denominator by x squared, because that's x raised to the largest power in the denominator. Let's just show it. The limit as x goes to infinity of x over x squared plus 4. So we want to divide the numerator by x squared and also the denominator by x squared. So that will give us the limit as x goes to infinity of x over x squared divided by x squared over x squared plus 4 over x squared. And if we simplify this, we'll have the limit as x goes to infinity, and in the numerator we'll have 1 over x divided by 1 plus 4 over x squared. This 1 over x term, as x goes to infinity, this will go to 0. The same is true of this 4 over x squared term in the denominator. That one will also go to 0. So our limit will end up being 0 over 1 plus 0, which is equal to 0. Here we computed the limit as x goes to positive infinity, but if you compute the limit as x goes to negative infinity, you'll get the same thing. In general, for a rational function, p over q, if the degree of the denominator is larger than the degree of the numerator, then the limit as x goes to either infinity or negative infinity of px over qx will be 0. So there will always be a horizontal asymptote, y equals 0, provided the degree of the denominator is larger than the degree of the numerator. Let's do another example. Sketch the graph of f at x equals 3x squared plus 1 divided by x squared minus 4. So this is a rational function where the degree in the numerator is the same as the degree in the denominator. So for step 1, we want to determine the x and y intercepts and the vertical asymptotes. The vertical asymptotes, of course, are when you're dividing by 0, and that's easy to pick out in this case. So we have vertical asymptotes when x squared minus 4 is equal to 0. Well, that's just x equals plus or minus 2. Now what about the intercepts? Well, the y-intercept, that's just when x is equal to 0. And when x is equal to 0, y is equal to f at 0, which is 3 times 0 squared, which is 0 plus 1, over 0 squared, which is 0 minus 4, which is a negative 1/4. So the y-intercept is 0 comma minus 1/4. What about the x-intercepts? Well, it turns out that there aren't any in this case. There are none. And why is that? You get an x-intercept precisely when y is equal to 0. So that means 0 is equal to 3x squared plus 1 over x squared minus 4. Can that happen? Well, that can only happen, you can only have a rational function being equal to 0 when the numerator is equal to 0. But 3x squared plus 1 is always strictly greater than 0. 3x squared is always greater than or equal to 0, and then if you add 1 to it, you're going to get something which is always bigger than or equal to 1. So in particular, it's never equal to 0. So there are no x-intercepts. That brings us to step 2. Let's determine the critical numbers. So in order to do that, we need to differentiate f. So f prime is going to be the derivative of this quotient, the derivative with respect to x of 3x squared minus 1 over x squared minus 4. So we just differentiate this using the quotient rule. So the derivative of the top is going to be 6x times the bottom minus the top, 3x squared minus 1, times the derivative of the bottom, which is just 2x. And all of this is divided by the bottom squared. So x squared minus 4 quantity squared. So now we simplify this, or at least the numerator. So we'll have 6x cubed minus 6 times 4 is 24x, and then we're going to have a minus 6x cubed, and then plus 2x. Okay, and all of this is divided by x squared minus 4 quantity squared. And we'll notice right away that this 6x cubed cancels with that 6x cubed, and we'll be left with a negative 24x plus 2x. So that tells us that f prime of x is equal to negative 22x over x squared minus 4 quantity squared. We need to determine when this is equal to 0 or when it doesn't exist. It doesn't exist when you're dividing by 0, but that's precisely when x is equal to 2 or negative 2, and those aren't points on the graph anyway, those are the vertical asymptotes, so we don't need to consider that. We only need to consider when this is equal to 0. So we note f prime at x is equal to 0 when x is equal to 0. So x equals 0 is our only critical point. Of course, we also want to find the y value that goes along with that. So y is equal to f at 0, but of course that's just 0 plus 1 over 0 minus 4, which is negative 1/4. This isn't a surprise because we already computed our y-intercept, and that's when x is equal to 0. So we already knew that that was the answer. So the critical point on the graph is 0 comma minus 1/4. Now what we would like to do at this point is plot it on the graph. And this is our step 4, but we're going to save all of the plotting until the end. So instead we're just going to go straight to 5, which is determine when this function is increasing and decreasing. And in particular, that will tell us whether or not this critical point is a local maximum or a local minimum or neither of those things. So we need to make a number line so we can make a sign chart. And on this sign chart, we're going to put 0. Now, it's not enough just to put 0. You also need to include the vertical asymptotes because you're trying to determine if the function is increasing or decreasing. And that can change at an asymptote. It can jump from increasing to decreasing. So just in case, let's just put in negative 2 here and positive 2 here. So these are our vertical asymptotes. So I'll just put dotted lines here so that way we remember what they are. So this gives us a total of 4 intervals that we have to check. And we just need to check the sign of the derivative at one point on these intervals. Now, this is not difficult to do because our derivative, which you see right here, this is our derivative. Notice that the denominator is always positive. It's just the numerator that might be negative or positive. So the numerator determines the sign. And notice that it's negative 22x. So if x is positive, then the derivative is negative. So anytime you're to the right of 0, you're going to end up with a negative derivative. So if the derivative is on the top here, then you're going to end up with a negative wherever x is positive. And you're going to end up with a positive wherever x is negative. So if f prime is on top, then we put the f down here. And so wherever f prime is positive, your function is increasing. And then when your derivative is negative, your function is decreasing, like so. So what that tells us is that the graph of this function is increasing to the left of negative 2. So it's going to look something like that. Then you're going to have an asymptote, and then it's going to be increasing and then decreasing, and right here this is going to be where x is equal to 0. So you're going to have a local maximum there, and then you're going to have another asymptote, and then after that it's going to be decreasing. So it's going to look something like that. Now this is just our first sketch. We need a little bit more information to see exactly what it's going to look like. And for that we move on to 6, where we compute the second derivative and determine the concavity. So f prime prime of x, well, that's going to be the derivative of the first derivative. So it's going to be the derivative with respect to x of negative 22x over x squared minus 4 quantity squared. And it's at this point that I notice that I made a minus sign error earlier on. So if we go back to our original derivative here, there's actually supposed to be a plus here. If you look at our original function, it's 3x squared plus 1. I just accidentally wrote a minus 1 there. What does that mean? Well, it doesn't mean a whole lot for us. It means that that's a plus, and it actually means that this is a minus. So instead of minus 22, we're actually going to have minus 26x. But since we were only checking to see if the sign was positive or negative, the fact that we had written a 22 there instead of a 26 isn't really a big deal. However, let's go back and change this one to 26. Okay, so this is what we want to differentiate. Okay, so we're going to compute the derivative of the numerator. So that will be a minus 26 times the denominator, which is x squared minus 4 quantity squared, minus the numerator, minus 26x, times the denominator, or the derivative of the denominator. So that's going to be times 2 times x squared minus 4 to the 1 times 2x. And all of this will be divided by the denominator, x squared minus 4 squared, quantity squared. So that'll be to the 4th. Now all of this right here, all of this term, that's the derivative of the denominator. That's the derivative of the denominator. It's something to the squared, something to the 2 power. So you use the power rule, and it's going to be 2 times that thing to the 1 times the derivative of whatever's inside. So the derivative of x squared minus 4 is 2x. Okay, so now what we're going to want to do is we're going to simplify this a bit. And let's notice that we can just factor out a few things. So there's a negative 26 here and a negative 26 there, so we can factor that out. But also we have an x squared minus 4 here, and we have 2 of them here, so we could factor out one of those. So this is going to be equal to negative 26 times x squared minus 4. All right, so that's what we're factoring out, and then we're going to multiply that by whatever's left behind. So we're going to have one more x squared minus 4 here, and then we're going to subtract. And what are we going to subtract? Well, we have an x here. We factored out this minus 26. So let's see, what else do we have? We're leaving this x behind, and we're leaving that 2 behind and that 2x behind. So that's going to give us 4x squared. 4x squared, like so. And all of this is divided by x squared minus 4 raised to the 4th. Okay, and now the next thing that we notice is that we have an x squared minus 4 here, and we have 4 of them here, so we can just cancel out with one of them. And so we're going to end up with the opposite of 26, or negative 26, and then the x squared minus 4 is going to disappear, and we'll be left with whatever's inside these parentheses. So we have an x squared minus 4x squared, so that's going to give us a negative 3x squared minus 4, and all of that is divided by x squared minus 4 cubed. So our objective is to determine whether or not our second derivative is positive or negative. And the first step is to determine the places where it's equal to 0 and the places where it's undefined. So let me just rewrite this. F prime prime of x is equal to, what I'm going to do is I'm just going to take that minus sign and run it back through here. So we'll end up with 26 times 3x squared plus 4. And all of this is divided by x squared minus 4 quantity cubed. Okay, now what you'll notice about this is there's no place where this is ever equal to 0. So this is never equal to 0. The numerator is 26 times some quantity which is 3x squared plus 4. So this factor here is never 0. It's always bigger than or equal to 4, so it's never equal to 0. The denominator can be positive or it can be negative because we've got a cube here. But the thing is, the denominator can never make your rational expression 0. It can make it undefined. And it's undefined, f prime prime of x is undefined when the denominator is equal to 0. So that's when x is equal to plus or minus 2. Now these are the vertical asymptotes, so your function isn't defined there anyway. But the concavity can change at an asymptote, and we'll see that here. Let's just make a sign chart. So this is a sign chart for the second derivative, and we want to know what that tells us about the concavity of f. So we need to mark the asymptotes. Again, there's no place where this second derivative is equal to 0. So in particular, that means there are no points of inflection. And yet the concavity will change. So for example, we can look to the left of negative 2, and we can pick anything which is convenient. So for example, we can pick x equals negative 3 if we want. So f prime prime at negative 3, that's going to give us 26 times 3 times negative 3 squared, that's 9, plus 4, divided by, again, negative 3 quantity squared is 9, minus 4 cubed. And we don't need to know what the value is, but it's certainly positive. So that means the second derivative is positive on the leftmost interval. What about the middle interval? We can pick any convenient number, and 0 is in that middle interval, so let's just pick that. So f prime prime of 0, what's that going to give us? That's going to give us 26 times 0 plus 4 divided by 0 minus 4, so it's negative 4 quantity cubed. Negative 4 cubed is still a negative number, so that will be less than 0. So on that middle interval, the second derivative is negative. Now there's one more interval to check. The rightmost interval, the number's greater than 2, so we can just pick, for example, 3 again. So f prime prime of 3 is going to give us the same thing that we had with our first computation. It's 26 times 3 times 3 squared, so that's times 9 plus 4. And we're going to divide that by 3 squared is 9 minus 4 quantity cubed. So once again, that's greater than 0. So once you've determined the sign of the second derivative, that tells you the concavity. So that tells you that on the leftmost interval, f is concave up. On the middle one, it's concave down. And on the rightmost interval, it's concave up. So we can tell pretty much what the graph is going to look like now. We can draw our x-axes in here, or x-axis and our y-axis, and we know that the y-intercept is -1/4, which is right about there. And we know that there's going to be a vertical asymptote at x equals -2 and at x equals +2, like that and like that. And we know that the function has a local maximum at x equals 0. If we just scroll back a little bit, we know that there's a little maximum at x equals 0. So it's going to look something like this, and it's concave down, we know. So it's going to look something like that. And it's not going to reach these asymptotes. It's not going to cross those asymptotes. What about on the left side and the right side? Well, to the left of -2, we know that it's increasing. And to the right of 2, we know that it's decreasing. So it's on, let's look to the left, in the leftmost interval. It's increasing and it's concave up, so it's going to look something like that. And on the rightmost interval, it's decreasing and concave up, so it's going to look something like this. Now, there's one thing that we still need to determine, and that's the asymptotic behavior. Now, it's going to turn out that there is a horizontal asymptote here, but we need to determine what that is. So we can ask ourselves, what is the horizontal asymptote? So that's something we can figure out. This is a rational function, so we have a method already for doing that. Now, if we look at the graph, this is the actual graph, you can see that it's not far off from what we determined. And you can also guess what the horizontal asymptote is going to be. It looks like it's y equals 3, just based on what this graph looks like. Can we show that? And the answer is yes. We can show that using the method that we already described, dividing by x raised to the largest exponent that appears in the denominator, which in this case is x squared. Now, generally speaking, for a rational function p over q, if the degree of the denominator is the same as the degree of the numerator, then the limit as x approaches positive infinity or negative infinity of p over q is just the ratio of the leading coefficients. So you'll end up with a horizontal asymptote, which is y equals L, where L is this ratio of leading coefficients. And you can see that that's the case here. The leading coefficients are 3 in the numerator and 1 in the denominator. So the limit is going to be 3, and we can show that using the method we already described. So the limit as x goes to infinity of 3x squared plus 1 over x squared minus 4, you divide by the largest power that appears in the denominator, which is x squared. Divide both the top and the bottom. So we'll end up with the limit as x goes to infinity of, so in the numerator we'll have 3x squared over x squared plus 1 over x squared. And then in the denominator, you'll have x squared over x squared minus 4 over x squared. And so you get some cancellation here. This x squared cancels with that x squared, this x squared will cancel with that x squared, and you'll be left with the limit as x goes to infinity of 3 plus 1 over x squared divided by 1 minus 4 over x squared. And the 1 over x squared term, that goes to 0, and the 4 over x squared term, that also goes to 0. So what are you left with? 3 over 1. Or in other words, 3. Now here we computed the limit as x goes to positive infinity, but if x was going to negative infinity, it would be exactly the same computation. Let's do another example where we sketch a rational function. This time the degree in the numerator is greater than the degree in the denominator. So let's see how that affects things in the long-term behavior, that is, asymptotically. Well, the first thing we want to do is we want to find the intercepts. So we have the y-intercept is where x is equal to 0. And of course, in that case, we're going to have y is equal to f at 0. That's just going to be 0 squared over 0 minus 1, which is just 0. So our y-intercept is 0, comma 0. And that's also the x-intercept. So that's the same. What about the vertical asymptotes? Well, we have 1, and that's where x is equal to 1, because we're dividing by 0 when x is equal to 1. Next, we want to compute the derivative. So f prime of x is the derivative of quotient, the derivative with respect to x of x squared over x minus 1. So that's going to be the derivative of the top times the bottom minus the top times the derivative of the bottom, which is just going to be 1. And it's divided by the bottom squared. So that's going to give us a 2x squared minus 2x minus x squared over x minus 1 quantity squared. So that's going to give us 2x squared minus x squared is 1x squared. So we'll have 1x squared minus 2x divided by x minus 1 squared. And you can actually factor out x in the numerator, so you'll end up with f prime of x is equal to x times x minus 2 over x minus 1 quantity squared. Now this doesn't exist when x is equal to 1, but x equals 1 is a vertical asymptote, so we don't have to worry about that. So instead, we just look at where f prime of x is equal to 0, and of course that happens when x is equal to 0 and when x is equal to 2. So those give us 2 critical points. We also want to find the y values that correspond to those. So we have for x equals 0, well, we already know that. Y is equal to f at 0, that's just 0. So that gives us 1 critical point with coordinates 0, comma 0. And that's, of course, the x and y intercept as well. And then we're also going to have x equals 2. And that's going to be y is equal to f at 2, which is 2 squared, which is 4 over 2 minus 1, which is 1, so it's just going to be 4. So that gives us our second one at 2 comma 4. So these are our 2 critical points. We want to determine if they belong to local maxima or minima, and we can figure that out when we look at a sign chart for the first derivative. We'll just remind ourselves that step 4 here would be to plot these, but we'll do that later. So that gives us step 5, where we look at a sign chart for f prime. Now we have to put 3 things on here. We have to put x equals 0, x equals 1, and x equals 2. X equals 0 and x equals 2 are on here because that's when the derivative is 0. But we also have this vertical asymptote here, and we need to have that in here as well. The next step is just to determine the sign of f prime and how that relates to f. So we have 4 intervals that we have to check, and so you can just pick any number in these intervals. So for example, we can pick, let's start to the left of 0, so we'll just look at f prime at -1, and we just need to determine if it's positive or negative. So we're going to have a -1 times a -3 over something squared. So it'll be -2 squared. So the denominator will be positive. So we're going to end up with something which is positive. And then we need to pick something between 0 and 1. So we'll just pick 1/2. We'll do the trick. So then we're going to end up with 1/2 times a negative 3 halves over negative 1 half squared, and that's negative altogether. And then we check f prime at 3 halves, that's between 1 and 2. So that's going to give us 3 halves times 3 halves is 1 and a half minus 2, that's a negative 1 half, divided by 3 halves minus 1 is 1 half squared, and that of course is still negative, so we're going to have a negative there. And then finally we just need to check at f prime at some value bigger than 2. Let me just move all of these up just a little bit so I have a little bit more room on this slide. So then we'll just do f prime, and you can pick any number that you want that's bigger than 2. So 3 is convenient. So we'll have 3 times 3 minus 2 divided by 3 minus 1 squared. And of course, that's 3/4, but really what we care about is that that's positive. So that tells us that the function is increasing, then decreasing, then decreasing, then increasing. Okay, well, the next step is to figure out the concavity. So we'll do that. Now, in order to do that, we need to compute f prime prime of x. And this is going to be the derivative with respect to x of x squared minus 2x divided by x minus 1 quantity squared. So the derivative of the top is 2x minus 2 times the bottom, x minus 1 quantity squared, minus the top, x squared minus 2x, times the derivative of the bottom, and use the chain rule. It's 2 times x minus 1. And we're going to divide all of that by x minus 1 quantity squared. So the first thing that we might notice is that 2x minus 2 is the same thing as 2 times x minus 1. So you can factor that out. So what are we going to have? We're going to have that this is equal to, if we factor that out, we'll have 2 times x minus 1. And what's left behind is an x minus 1 quantity squared. That's from here. So this term is that term. And then we're going to subtract an x squared minus 2x. And all of this is divided by x minus 1 quantity squared, which just for fun I'm going to write as x minus 1 times x minus 1. Because what I'm about to do is I'm about to take that x minus 1 and cancel it with one of those. So then we're going to have a 2 times, and in the brackets we're going to have x squared minus 2x plus 1 minus x squared plus 2x. And all of this is divided by x minus 1. And we'll notice that there's an x squared minus an x squared, 2x minus 2x. The only thing that's left over is that 1. Now, of course, this is where we notice that we made a small mistake with our denominator, because, of course, that's x minus 1 squared quantity squared. So really, there should be a 3 there and a 3 there. Okay, so that tells us that the second derivative is 2 over x minus 1 cubed, like so. Okay, so what are we going to do with this second derivative? Well, we need to make a sign chart. Now you'll notice that there are no places where f double prime is equal to 0. There are no points of inflection here. So this value right here, this is never equal to 0. So there are no points of inflection. But you do not need to check the sign of the derivative at the vertical asymptote. So let's just put that in here. We want to check f prime prime. So we just need to check something less than 1, so 0 will do. So f prime prime at 0, and that will give you 2 over negative 1 cubed, which of course is negative 2. So that's less than 0, so we just put a minus sign here. And then f prime prime, just pick something bigger than 1. So 2 would be fine, because then we'd have 2 over 2 minus 1 is a positive 1 cubed, and that's of course just 2, so that's positive. So our function f goes from being concave down to being concave up. Now notice there are no points of inflection here, but the concavity does change at the vertical asymptote. That's because there's no continuity at the vertical asymptote, so it can jump around, it can do all kinds of things. So now we have some idea of what the graph will look like, and we can just sort of guess what it'll look like here. And what do we know? We know it passes through the point 0, 0. We know that at 1 there's a vertical asymptote, like so. And we know that we have a critical point at 2, and that's when y is equal to 4, so it's going to be up here somewhere. So let's just put it right there. So that's 2 comma 4. And we know it's passing through 0 comma 0. And what do we know? We know that there's a local maximum at 0 and a local minimum at 2. Well, let's just double check that we know that. If we go back here, we can see that at 0 that there's a local maximum. It's looking like that. And at 2 there's a local minimum. So it's going to look something like that, and something like that, and something like that. Now we also know that it's concave down over here to the left of 1, and it's concave up to the right. We also have a vertical asymptote, so it's not going to cross that. So it's going to look something like that. Notice that just based on what we know, we can tell what the limit is as x goes to infinity or minus infinity. So the limit as x goes to infinity of this function, f at x, well, we know that this function is concave up, and we know that it's increasing. So that means it's just going to keep going. So this is going to be infinite. And we also know that the limit as x goes to negative infinity of f at x is going to be minus infinity. And we know that because the function is concave down and decreasing. So because of that, we know that it's the concavity is what tells us that it's going to be minus infinity. But we can compute this directly. First, let's just take a look at the graph, and we can see that we had basically the right idea here. Maybe our graph wasn't as good as this one, but we had basically the right shape. But let's actually just compute the limit. So let's make a quick remark. For a rational function p over q, if the degree of the numerator is larger than the degree of the denominator, then you can be sure that the limit as x goes to positive infinity or minus infinity of p over q is either positive infinity or minus infinity, but you don't know until you actually look at your specific example. So in particular, there's no horizontal asymptote. However, if the degree of the numerator is exactly one more than the degree of the denominator, which is what we have in our example, then the graph will have what is called a slant or oblique asymptote. So our example, we have y equals x squared over x minus 1. And that has a slant asymptote of y equals 1 plus x. And how can you show that? Well, you can use polynomial division. So using that, it's possible to show that x squared over x minus 1 is x plus 1 plus 1 over x minus 1. And we can just do that by dividing x minus 1 into x squared. So in order to do that, you need to put up here the thing that you need to multiply by x minus 1 to get x squared. So that's going to be an x. So x times x minus 1 is x squared minus x. So then you just compute the difference of these things. So the x comes down, and so then it's going to be plus 1. And so that's going to give you 1 times x minus 1 is x minus 1. And then you compute the difference, and that's just going to give you a 1, and that's your remainder. So you're going to have that x minus 1 dividing into x squared is going to give you x plus 1, which is this part of the quotient, plus the remainder, which is 1 over x minus 1. Now, basically, what this tells you is that the limit as x goes to infinity of x squared over x minus 1, well, certainly it's going to be equal to infinity. We can see that because 1 over x minus 1, this part's going to go to 0. So you're just going to have x plus 1, and x is going to infinity. Now, similarly, the limit as x goes to negative infinity of x squared over x minus 1, well, that's going to be negative infinity. And again, we can see that by looking at this, because the 1 over x minus 1 goes to 0, and you're just left with x plus 1, and x is going to negative infinity. So you can see that it's going to infinity or negative infinity, but more to the point, you can also see that as x goes out to infinity or minus infinity, this remainder term, that gets incredibly small. So this goes to 0. So that means it doesn't contribute very much. So as x goes out to infinity or minus infinity, so as you're moving far to the right or to the left, your expression looks a lot like x plus 1. It's x plus 1 plus a little something which is tiny. So it starts behaving like x plus 1. And in fact, if you look at our graph again, this line right here, this is y equals x plus 1. And that's our slant or oblique asymptote. A slant or oblique asymptote indicates that the asymptotic behavior of a rational function is linear. Now this happens when the degree of the numerator is exactly 1 greater than the degree of the denominator. If the degree of the numerator is greater than the degree of the denominator by more than 1, then we can still identify asymptotic behavior as x goes to plus infinity or minus infinity, but it might not be linear anymore. For example, if we look at the graph of y equals x cubed over x minus 1, this is the same as our previous example, but we've increased the exponent from 2 to 3. In this case, it's asymptotic not to a line, but to a parabola. We can show, using polynomial division, that x cubed over x minus 1 is equal to x squared plus x plus 1 plus 1 over x minus 1. Now, we won't actually do that. It's similar to the example we did before. It just has one extra term in it. But just like before, this 1 over x minus 1 term, this goes to 0 as x goes to infinity or minus infinity. So what you end up with is that x cubed over x minus 1, as x goes to infinity or minus infinity, starts looking like the parabola y equals x squared plus x plus 1. And we can actually see that if we look at the graph. The solid graph that you see here, this is the graph of the function y equals x cubed over x minus 1. And this dashed graph is the graph of the parabola. So this graph right here, this is the graph of the parabola y equals x squared plus x plus 1. So you can have nonlinear asymptotic behavior with two curves getting really close to each other without one of them being a line. And as you can see from the graph, you don't even have to go away from x equals 0 very far before these two graphs start getting very close to one another.